Welcome! Today I'm going to introduce the SDCOM to you. This is the SDCOM, which is a specialized crystal orientation diffractometer. I'm going to open it up right now. So on this side we have our 30-watt tube, and on this side we have two scintillation detectors. The SDCOM mainly measures in the azimuthal scan mode, which means we will move the tube and detector to one angle per material and orientation, and then rotate the sample on this stage here. So you can see it's a pretty big stage. We can put large samples on here, no problem. The whole coniometer moves up and down to accommodate various heights of sample. So we need some sensors to make sure we're actually aligned on the sample in the height. First, here is a height sensor that has a small laser spot here and a camera to recognize where it is. Then, because this is only one small spot and we might miss the sample, there is a light bridge between here and here that will detect when we are close to the table and make sure we don't crash. Now, there's another laser up here, and that produces the laser cross. So if I block it, the cross down there disappears. This is so we can see where we are on the sample and can accurately position where we will measure. In the system there's one more laser, which is up front here. That's the wobble laser. Now say maybe the table is not aligned exactly flat, or the top and bottom of the sample are not entirely parallel. This laser will correct for it. We shine a laser onto the sample, and that's reflected into this mirror back here, and then it goes into a camera. The position in the camera of the laser in the camera will change depending on the tilt and rotation, so we can figure out what the tilt on the sample is and correct for that. Okay, so this is a specialized crystal orientation diffractometer, and it can measure the orientation of a crystal very fast. One rotation of the table takes 5 seconds. We do one warm-up lap, so the measurement starts at 10 seconds, at which point we already have a pretty good accuracy. But if you want more accuracy, we can measure longer. If you want an accuracy that's twice as good, we need to measure 4 times as long. So if you want a measurement like that, we are talking 25 seconds. Okay, now let's actually measure a sample. I've got a calcium fluoride octahedron here, and I'm just going to place it on the table, just like this. And then we're going to have to do the height alignment. Since calcium fluoride is completely transparent, the laser dot will not be visible on the sample. The height sensor cannot find it. We need to put a piece of paper on top of the sample to do the height alignment. We have to close the system, otherwise the mechanics won't move, and then I tell the system to move the sample. Now the angle adjusts, so the laser sensor can easily be aimed onto the sample. And it moves down. Now sees that it's close, it moves slowly, and there it's found the height and turned back into the measurement direction. We remove our piece of paper again. Close the system, and now we're going to start our measurement. In just a second while the generator switches on. Now the goniometer is going to move into the correct angles. Now our measurement is run, so let's go have a look at the results. Now we have our result. From this peak pattern down here, the system calculates the tilt direction, reference offset. Comp 0 and comp 90 are the Cartesian representations of the tilt. So we have a diagram here that shows this a bit more clearly. Down here, this gray bar is the reference bar on the table, and this red arrow is where the tilt is pointing. Now I've set the system to use the -1, -1, 2 direction as a reference direction, so it calculates the angle from that one. This is because it's not so easy to align the sample to the bar in the same way every time. This gives a more consistent result. We can see that the Yeah, so that we're almost 90 degrees away from the -1, -1, 2 direction, and the angle between the -1, -1, 2, and the center position on the bar here is 4.7 degrees. That was measured here. So we can also very accurately measure all these in-plane directions. With many other X-ray crystal alignment techniques, you would only get where's this the tilt pointing, but you would not get all these other crystal directions at the same time. Okay, now we're going to measure a more typical sample, a silicon carbide wafer. First, I'll have to take the old sample out. Then I've got my silicon carbide wafer. Place it on the stage, and I'm aligning it to the flat here. All right. We'll have to do a height adjustment again, so we'll need our trusty piece of paper. And we're going to move to the sample. So now we're almost ready to measure, but we need to select the correct recipe, which is silicon carbide 4HC. And then we can rename our measurement just by pressing this button. It gets the same name as the recipe. And then we're ready to start the measurement. Switch on the generator, takes a second. And now we're also using our camera to measure the tilt of the wafer. So you can see this dot moving around, and it's currently moving in the ellipse, which tells the software the tilt of the combination of the stage and the wafer. So it only records that during the first run. You can close that again. Now we see that this measurement is taking a bit longer. We're now doing a 4 rotation measurement for higher accuracy. And there we go. We've got our laser tilt correction, a minor one, which amounts to about 1/100th of a degree in the direction 76 degrees away from the reference flat. The tilt of our sample is 4.2 degrees, 90 degrees away from the reference bar, and the reference offset, so the angle between the 010 axis and the bar is 0.3 degrees, as it should be. That was the silicon carbide wafer. Now we're going to do something different. We're going to measure some very small diamond samples. I'm going to raise up the system, and we're going to use this small sample, horizontal small sample holder. And then we have our diamond sample. Perhaps you can see it, it is really tiny. So even with our small sample holder, I need to also put in a part of a microscope slide so the sample does not disappear into the sample holder. Okay, so we've got that. Diamond, align it to just to the flat. Let's have a close look. Okay. Place it in the center with the laser cross, and then adjusting the stop bar inwards, so about here. Tighten it, align this one. Then we need our trusty piece of paper again. All right. Close the system. We've done our height alignment. Now we need to select our Diamond 001 recipe. Again, take over that name, and then we can measure. So, in this case, we've got about 3 degrees of tilt in the almost directly in the -1, -1, direction, which is the reference direction in this case. And there's only a very small angle of 0.53 degrees between the bar and that flat in this case. So this was the SDCOM crystal orientation diffractometer. As you've seen, we can measure any single crystal, whether this is a bulk sample or a tiny sample down to 2 by 2 millimeters, or wafers up to 300 millimeters in diameter. It is quite easy and fast to measure anything with a high accuracy. So, with that, I would like to thank you for watching, and if you have any questions, feel free to reach out to us.